Thank you and good afternoon, Science for All. A pleasure to be here to tell you about the weird world of the very, very small. So I'm going to be starting just briefly to give you a little sense of scale, because we're going to go from the human scale of meters down to millimeters and then divide by 1,000 down to microns and then divide by 1,000 down to nanometers. And along the way, we're going to ask, what is the world made of? And can we tell from a sense of symmetry what is actually going on inside materials, inside us, effectively? And I'll finish by saying, well, the quantum world is pretty weird. And we're going to finish by saying, well, it is weird, but we can actually use the quantum world to actually look at the quantum world. In other words, we're going to be imaging some atoms right at the end there. So we're used to the idea of interacting with each other and the world on a fairly macroscopic scale. And of course, most of us with reasonable eyesight can see objects down to sort of millimeter size. So we're used to the idea of seeing objects down to this sort of scale. And you can even see objects on this sort of scale. I'm not sure you recognize what this is. Pollen. Well done. It's a pollen grain. Typically somewhere of order a 10th or a 20th of a millimeter, so about 50 microns. Remember, a micron being 1,000th of a millimeter. So that's about the smallest thing we can actually see with the naked eye, but of course microscopes will allow us to see things smaller. And that's a natural structure, but that doesn't stop us actually making things on smaller scales. In terms of mechanical structures, we can make mechanical structures like this ratchet system and cogs, etc., again, on spatial scales of order tens of microns, way too small to actually see. But of course, if we want to think about things we've made on the very smallest scales, we go beyond mechanical structures and we start thinking about electronic structures. When we're making bits of semiconductor, when we're making computer chips, regardless of what those chips actually do, then for every square millimeter of silicon in which we want to put a whole load of transistors, either for a computing unit or for a memory unit or whatever it may be, we can get literally hundreds of millions of transistors in something that size. So if you think of a chip that might be a square centimeter, we're now talking easily about being able to put billions of transistors onto a piece of silicon, which is barely the size of your thumbnail. That means each of the individual components inside these devices is only of order nanometers or perhaps tens of nanometers in size. So we're already at the point where we can manufacture things on a spatial scale that's some million times smaller than the scale that we are used to. And as you can appreciate, we're already getting to the point where the things that we are making in electronic circuits are not that much bigger than atoms. So let's think about structure. We can ask the question, which of course we've been asking for thousands of years, what's the world made of? How can we tell what it's made of? And what sort of clues do we have in terms of the makeup of individual things around us? Well, you can take a number of different approaches. One approach is to say, well, everything is just made of earth, air, fire, and water. Well, yeah. If only physics was that simple, it would be a lot easier and it wouldn't take a 3-year degree to teach to undergraduates. If it was that simple, life would be really great. But unfortunately, it is a little more complex than that. And rather than saying, wouldn't it be nice if everything was just made of earth, air, fire, and water, Galileo came along in the 1600s and said, that's not really what we should be asking. We shouldn't be trying to work out how things should behave or how things should be. We should actually do experiments and find out how they actually are. He arguably was the first person to propose experimental evidence as being more important than simply asking how things should be. So we shouldn't be asking what should happen if I drop this cannonball or I roll this down the hill or I bang through things together. Rather than asking what should happen, let's actually try and answer the question, what actually happens? So the first true scientist interested in experimental results rather than purely theory. And not that many years later, along came Newton in the middle of the 1600s, who then effectively tried to pull a lot of these strands of thought together and say, Right, we know to some extent how the world works. We can see the moon appears to go round the Earth. And if I drop an apple, it drops to the ground. So he started formulating ideas like a law of universal gravity, as well as something like, let me just get a couple of props out for the sake of it here, as well as if we've got a couple of objects, it doesn't matter whether they're snooker balls or golf balls, what happens if we bang them into each other? What happens if it rolls on a table? Let's think about how things actually behave. You might think that things move and then naturally come to a stop. But Newton said, no, things will continue moving until you stop them with friction or air resistance or something else, some other force. He turned people's ideas around to try and explain not only how golf balls bang into each other and how they behave, but something on a more universal scale, how gravity works. He also did a number of experiments talking about the nature of light. So he was not only talking about how particles of matter behave, but also how light behaves. And that's rather important for what we are going to be talking about in terms of how the world is put together. So Newton basically envisaged a clockwork universe. Doesn't matter how it came to be, doesn't matter how it came into being in the first place, whatever that prime mover was. Basically, if you've got a universe, it's clockwork, you wind it up, it just goes. So planets go round the sun, for instance, and we've got an idea, okay, we've got a model now of universal gravity that says why the planets are in circular or perhaps elliptical orbits. And we can work out what's going to happen to the Earth in the future. The Earth takes a year to go round the sun, and we are pretty damn sure that in 6 months' time, the Earth is going to be on the other side of its orbit. And in a year's time, the Earth will come back to where it started. And in 10 years' time, we can predict where the Earth is going to be. And in 100 years' time, we can predict where the Earth is going to be. Everything is deterministic. Everything is clockwork. That was the universe of Newton. And when we look at what the world is made of, for instance, if we look at snowflakes, we say, well, they all appear to be different, but they all seem to have six-fold symmetry. You can take them, rotate by 1/6 of a revolution, and you get the same shape back. So if all snowflakes are made of ice, and ice always seems to have this six-fold pattern, surely that is telling us something about what makes up snowflakes. And can we apply that same logic to other structures? If we want to know what we are made of, or what cats are made of, or what golf balls are made of, or what this table is made of, can we get clues by looking at how they're put together? Well, this tells us something about there is some property of ice that makes it want to be six-fold. And if we look at other crystals, we get other clues. This just happens to be another metal. It doesn't really matter which one. It happens to be bismuth. When bismuth melts and then solidifies again, it solidifies into rather interesting looking structures, which must be telling us something about what are the building blocks that make a piece of bismuth. And similarly, other compounds. They might be elements as we understand them today, or combinations of elements. More recently, we've actually made metals that seem to want to crystallize into very odd forms. You might say, well, it's perfectly reasonable if the universe is made of little Lego bricks that it might want to actually form cubic structures like on the left-hand side. But what on earth would make something want to crystallize into a dodecahedron? What are the building blocks? If they're still the same Lego bricks, why do they want to form a dodecahedron with pentagonal faces? That must be telling us something about the underlying structure that wants to form this particular crystal. So we have clues simply by looking around us, usually under our feet. We have the clues that tell us what the world is made of. But of course, it takes quite a while to actually unravel those clues. So here's a very rough timeline. I'm not going to go through the details, but here's 3 centuries of people who started thinking about what the world is made of. Way over on the left-hand side there's Democritus, who said, well, the universe is made of indivisible building blocks, let's call them atoms. And so we figured that the world is made of atoms, but we didn't necessarily know what atoms actually were for quite a while. And then centuries of work, often involving alchemy. In other words, let's take this particular compound, mix it or react it with this, and a certain number of grams of this, when reacted with that, gives a certain number of grams of that. If you do enough chemical reactions, you start to get an idea of what makes up what. So I don't know if your history of science is any good, but there's a few people here and you may recognize some of the names. So perhaps you recognize the second one because we've already mentioned him, Sir Isaac Newton. But the first one there is Boyle. Then we've got Newton. Do you recognize the next one? Lavoisier. And then we have Dalton. And then we have Avogadro. And then we have Maxwell. And then we have Boltzmann. I'm not going to go into the contributions of all of these scientists because each of them made an important contribution to our understanding of what are these atom thingies, how do they make up molecules, and how does that explain the chemical reactions that we've been looking at for the last 3 centuries. In particular, between 1800 and 1900, a couple of key experiments were carried out, which is important for what we're going to talk about shortly. And that is, in the early 1800s, Young did an experiment with light by shining light through slits. He showed that light interferes with itself, just like water waves do on the surface of the ocean. So basically, he concluded that light is a wave. And here we're using light in the broadest sense, not necessarily just visible light, with the experiments that he did, but we now know that applies to all wavelengths of light. So X-rays, gamma rays, as well as ultraviolet and visible and infrared and microwave and radio. So we now call it the entire electromagnetic spectrum, but at the time it was simply light is a wave. And some decades later, in the 1870s, J.J. Thomson found a particle which eventually became known as the electron. So we have a particle, and we can ask ourselves, well, this must have some rather important role to play in making up atoms. We're not sure how. An electron is negatively charged. Atoms don't have any charge on the whole. Therefore, there must be some positive charge around which we haven't found yet. And if we put positive charge and negative charge together, we can start to think about making these building blocks called atoms. So in the 1800s, it seemed reasonably well established. Stuff, i.e. particles, are, well, we've got electrons and a few other particles we have yet to find, and light is a wave. So we have particles, we have waves. Everything seemed hunky-dory. But as we move from the 1900s into the 20th century, then we have a problem. The next 30 years are complete and utter chaos where people are trying to really understand what's going on. And again, here are the key players. I'm not going to turn this into a history lesson, but here are the key players that had something to say about the nature of what an atom is and how are we supposed to describe the behavior of these tiny, tiny, tiny building blocks. So again, we'll just go through the names. I'm sure that some of these faces aren't necessarily familiar to you. Becquerel, who discovered radioactivity, and then we have Max Planck, Ernest Rutherford, who did experiments in Manchester, Einstein, I'm sure you all recognize, Niels Bohr, and then we have de Broglie, and the architects of quantum mechanics are Heisenberg and Schrödinger. So these 30 years or so, compared to the previous 3 centuries, was a very turbulent time. All sorts of things were learned about the nature of atoms. And again, I'm not going to go through all the details. There's simply a timeline saying some of the things that were actually popping up. Becquerel discovered radioactivity, so we now know that atoms can change and spit out other particles, which we need to understand. But one of the important turnarounds was the fact that along comes Planck and says, well, light isn't a wave, light is a particle. Up to this point, we thought that electrons and things like that were particles, and wave is a wave, and a light is a wave. But now along comes Planck and says, well, actually, light behaves like a particle. Not only that, but a little later, a couple of decades later, along comes de Broglie and says, well, actually, electrons aren't particles, electrons are waves. So we used to think that light was a wave and electrons were particles, and now they seem to be saying exactly the opposite, which is very embarrassing because a guy got a Nobel Prize for saying the first one, and now they're saying, well, actually, it's the other way around. Very embarrassing. And again, as well as, for instance, Rutherford saying, well, the atom from experiments appears to be a positively charged nucleus and negatively charged electrons. In other words, we now have an idea what the structure of the atom is. Here's our positive charge, here's our negative charge. That's why atoms are usually neutral, uncharged electrically. So now we've got an idea of the structure. But Again, a rather spanner in the works situation was Bohr and others like Max Born coming along and saying, we must bear in mind that nothing of what we're talking about in atoms are the clockwork atoms or the clockwork structures of Newton. We can't simply say that this is the way the atom is, and a fraction of a second later, if the nucleus of the atom is there and the electron is going around it, then we can simply plot out where the electron is, just like Earth going around the sun, and we know exactly what is going on. The key introduction in these roughly 1920s was the idea that probability contains a key role. We can talk about what is likely to happen, but we can't in any absolute sense say what is going to happen. And this is different from Newton, who says if you have two balls firing towards each other on a snooker table or whatever, when they hit, they are going to do this. You can say with absolute certainty how they are going to behave if you know how they're starting their motion. Whereas here we're saying, well, we can only talk about the probability of things happening. So a big sea change in how we think about the world. So this is perhaps the picture we have in what we think about when we say, what does an atom look like? That's sort of what most of us think of it. Even physicists tend to think of this occasionally, even if we know it's wrong. We tend to think of a little bunch of objects in the middle being positively charged and a whole load of electrons buzzing around the positively charged nucleus like bees in a beehive. That's wrong for so many different reasons, but it's still a nice little animated picture. Aesthetically, it's very pleasing. It's just a shame it's wrong. It's wrong for a number of reasons. One of the reasons it's wrong is because in this particular case, all the electrons look the same. They're all doing the same thing. They're all the same distance from the nucleus, so they would all have the same energy. But we know from experiments of what happens when we excite atoms and the light they emit, etc., we know that all of the electrons in any given atom aren't all at the same energy. So that picture should be replaced with something else. What sort of picture should we replace it with? Well, one option is to say, well, it's sort of like that previous one, but instead of having all the electrons the same, some electrons are close to the nucleus and some electrons are further out and some electrons are further out again. And even that picture is wrong because really atoms aren't two-dimensional, a bit like the solar system is essentially two-dimensional as far as the planets going around the sun is concerned. We really ought to think of an atom more like a shell of electrons orbiting around the nucleus. And here's the shell sort of cut in half so we can have a look inside. At least that gets around the problem that not all the electrons are the same. And lightweight atoms like hydrogen, helium, lithium, beryllium are not the same as heavy atoms, uranium, etc., because of the electrons that are further and further and further away from the nucleus. Notice that there are a certain number of coloured balls in each of these orbits. There are 2 in the inner one, and then there are 8, and then there are 18, etc. These numbers aren't arbitrary. These numbers are dictated by rules that we have come to learn from putting quantum theory together. In other words, during the early 1900s, examination of how atoms were behaving and putting together a model, at the time called the Bohr model, the Bohr model of the atom, told us that there's a certain rule that says you can put a certain number of electrons in each of these orbits. And if we do that, then we can start to explain why we have a periodic table of elements. We know there are 92 naturally occurring elements. We can see them by digging up and doing all sorts of chemistry. And we can understand why they have the properties they have if we understand that only certain numbers of electrons can go round a nucleus to make a certain type of atom. So again, we're not going to go through the properties of all 92 elements, but there's Mendeleev there at the top there, proudly saying, yes, we've now got an idea of why we have this particular structure of the behavior of atoms. It's all to do with counting electrons that are buzzing around the nucleus. But we shouldn't be fooled into thinking that that means it's clockwork, and all we have to do is to say, well, let's count the electrons and then sorted. We now know how atoms are going to behave. No, it tells us about certain properties of the atom, and it tells us why the properties of copper are not the same as the properties of iron, for instance, simply by counting up how many electrons are present. But we mustn't fool ourselves into thinking an atom is just a little bit of a flattened solar system. It is more complex than that, mainly because of this idea that we can't predict where things are going to be. We can't say if this was an electron going around a nucleus, not the Earth going around the sun, we can't say the electron is there now and it will be over here in another nanosecond, and if I ask where's it going to be in a microsecond, I can calculate it's going to be over here. That doesn't work. We have to resort to the idea that atoms are fuzzy. In other words, we can talk about where it's likely to be. So here are 6 representations of if we have an electron in an atom, we can't say where it absolutely is, but we can make this cloud brighter if it's likely to be here and darker if it's not likely to be here. Hence we end up with this fuzzy and rather odd-shaped clouds around a nucleus, which is at the center of each of these clouds. And these clouds represent where is an electron likely to be. Why do electrons behave this way? We don't know. Quantum theory says this is the way the world is. When we examine the world, we find it obeys this set of rules. Quantum theory, or quantum mechanics if you prefer. And it turns out that these are the structures of atoms. Structures in the sense of where are we likely to find the electron in any given atom. Every atom is different, and so this cloud will look a little different depending on which atom we are looking at. So when it comes with dealing with atoms, in the 1900s, 1910s, 1920s, they started saying, how are we going to build a model which allows us to say this is what an atom is doing, and that's why the atom behaves that way, and that's how atoms make molecules, and that's how molecules make us, effectively. We can do that by using, as I am now, a whole load of words. But the problem is words have more than one meaning. We can talk about particles and waves, but as we've already said, what we thought was a particle, like an electron, turns out to behave a bit like a wave. And when we look at waves like light, sometimes it appears to behave like particles. One joker once said, well, an electron behaves like a particle on Mondays, Wednesdays, and Fridays, and it behaves like a wave on Tuesdays, Thursdays, and Saturdays. What it does on Sunday, no one is too sure. But the problem is we're using these words as if we understand what they mean. And usually we do understand what they mean, because when we talk about a particle or an object, we normally think we understand what we mean by an object. It doesn't matter whether it's solid, liquid, gas, or something else. We think we know what we mean, but the words themselves can be misleading. And we've already seen that if we're talking about an electron that is orbiting a nucleus, it is not orbiting the nucleus in the same way that the Earth orbits the Sun. We're using the word, quite often we use the word orbital to try and make it distinct from orbits, but it is not the same. An electron doesn't orbit the nucleus in the same way that the Earth orbits the Sun. And we talk about spin as if we were talking about an electron spinning on its axis. But an electron doesn't spin in the same way that the Earth spins on its axis. So we're using common or garden words, but we're not meaning the same thing. And that's part of the problem. Words are ambiguous. And if we have to keep explaining what we mean by the words, it gets very difficult. So what's the alternative? Well, we don't try and understand atoms with words. Let's use pictures instead. But I've already said that pictures can be misleading. That's not what an atom actually looks like. That's just an artist's impression which looks nice and colourful. That is close in the sense that it is a representation of the probability of finding an electron at a particular point in space. But it doesn't really give us the big picture. Not least, it doesn't give us a three-dimensional picture. This is just a two-dimensional representation of what I'm talking about. So words aren't enough to describe the weird world of the very, very small, if we want to describe atoms. Words aren't enough, pictures aren't enough, and there's only one thing that actually works, and you're not going to like it, because the only thing that works is maths. This was what the scientists and the physicists and the mathematicians were doing in the 1910s, 20s, and 30s, trying to find a coherent structure, a framework that will allow us to describe what atoms are doing. And the mathematics That is just a tiny part of the mathematics involved in explaining how atoms behave. But of course, if we want to actually teach quantum mechanics to students, we can throw the maths at them, but that doesn't help. We've got to teach them the maths first, then explain how the maths tells you the right answer. But of course, in doing that, you've basically got to use words to talk to them, and usually your PowerPoints are very dull unless you put in a few pictures as well. So you've got to use words and pictures to back up the maths, but arguably it's only the maths that matters. If we want to understand how an atom works, if we want to understand, I want to know if I take this hydrogen atom and if I excite the electron to a higher energy state and I want to know what light will be emitted, I can calculate that. I can calculate the maths of what color of light will hydrogen produce. And I can calculate that to 10 decimal places. And the answer is right. The answer is it produces red light. We can do the experiment and quantum mechanics gives us the right answer. Explaining it in words is tricky. Drawing pictures is tricky, but the maths always gives you the right answer. And that's one of the problems with quantum mechanics. The maths is not trivial. We are not talking about kindergarten maths. It's not just knowing your times table. It's a little more complicated than that. And so students have to learn that before they can make sense of anything. And when you tell students you're going to have to learn this to understand quantum mechanics, the reaction is usually, what? Because when you look at it, it's the sort of maths that you might conceivably have touched on at A-level maths, but generally speaking, students won't have met this until they actually are told, we're going to need to develop this idea of maths because that's the only way of describing how this atom is going to behave or that molecule is going to behave. So you have to get used to the idea that if you want to understand this, you really have to do the maths first and then move on from that. And the architects of quantum mechanics knew that this was a problem. They said at the time, remember this is 100 years ago, we wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language. They were discussing with each other, how are we going to do this? What is the maths telling us? They were discussing and they realized that words do not convey everything we want to convey. When we're dealing with atoms, for instance, would it be better, rather than saying, well, this electron here is spinning and orbiting around the nucleus, would it be better to describe that by saying the slithy toes did gyre and gimble in the wave? Because you laugh, but they contain exactly the same amount of information. The first one only makes sense if I say, what do I mean by electron? What do I mean by orbit? What do I mean by spin? And what do I mean by atom? The same is true of the second sentence. If I explained what a tove was, what a gimbal is, and what a wave is, if I had to explain every part of it, in principle, I could convey the same amount of information. But we tend to go with the first one simply because it's English, and that's what they decided to do 100 years ago. If they had said the only way to explain how atoms behave is to invent an entire new vocabulary, then we wouldn't have some of the problems we now have in saying, well, that's not really an orbit, that's not really spin, that's not really doing what you think it's doing. But we're stuck with that. After 100 years, we've been using the English language to describe how atoms behave, and we've got to stick with that from now on. But physicists have said, rather remarkably, everything we call real is made of things that cannot be regarded as real. In other words, we regard that as being real, because I can't put my fist through it. Well, maybe next time. But it's made of atoms, and atoms are not really solid objects. They're just weird things which behave according to a set of mathematical rules. And atoms are made of things that we can't really pin down. Are they particles? Are they waves? Well, we don't really know, but how on earth can they make solid materials like this? Well, that's effectively what Bohr was saying here. Everything that we think of as being day-to-day real is actually made of stuff which we can't take those common sense ideas down to that level. Again, a rather striking statement from a physicist. Atomic physics has shown that atoms have no meaning. What? that can only be understood in experimental measurement. What Schrödinger was saying here is all that matters in quantum theory is we may not be able to visualize these atom thingamybobs. We may not be able to get a picture of them directly, but all that matters is we can apply the maths and we can get the answer of what would happen if we made a measurement. All I'm really interested in is if I make a measurement of this, what's the answer? If I put this together with that, what's the answer? If I add this atom to make a molecule, what is the result? Quantum mechanics tells us the result in a mathematical form, even if we find it difficult to interpret what it is it's telling us. He said, I don't like it. Sorry I ever had anything to do with it. This is the architect of quantum mechanics, which has stood for 100 years now as a mathematical model of how the universe works on the smallest of levels. But people were not happy. And the main problem with people not being happy at the time, or indeed not being happy in a quantum mechanics lecture when I'm trying to tell students about how this all works, is that quantum mechanics disagrees with common sense. Up to this point, we've always told students, when you do this calculation, see if the answer makes sense. When you try and work out how fast this snail is moving, if the answer is 10,000 miles an hour, you've probably done something wrong in your calculation. Use your gut instinct to tell you when you've done something wrong. You try doing that in quantum mechanics, it doesn't work, because quantum mechanics sometimes disagrees completely with common sense. For instance, atoms are unpredictable because they are only regulated by the mechanics of probability, not the deterministic mechanics of Newton. So we can only talk about how likely it is that something is going to happen. I can talk about the likelihood of this particular ball being in a particular position in space, or I can talk about the likelihood it having a particular speed. But I cannot say absolutely it is definitely here and it is definitely moving with this speed. We can only talk about things that are likely to be. And although we tend to think of atoms as quite small, actually they're not as such. If we remove everything in the universe except for one atom, which is a positively charged nucleus and a negatively charged electron, we can ask the question, what's the probability that that electron is at a given distance from the nucleus? And we can calculate that again to essentially any precision we like. We can say the likelihood that the electron is 1 nanometer away is this number, and we can calculate. What's the likelihood that that electron is 2 nanometers away? Well, it's a smaller number, but we can calculate that number. 10 nanometers, we can calculate it. A millimeter, we can calculate it. The probability of the electron being a certain distance from the nucleus goes down and down and down as we go further and further and further away. But it never hits 0. So in other words, there's a tiny likelihood that the electron in that atom is actually a centimeter away. There's a much smaller probability that that electron is actually at a distance of 1 meter, or a kilometer, or is in Australia, or is in Alpha Centauri. It is very, very, very unlikely, but the probability is not 0. So you can't say this atom is definitely this big. You can say the likelihood of the electron being this sort of distance is 99.9%, and you can say, I'm going to call that the size of the atom. That's fine. But you can't actually put an upper limit on size. The other weird thing is that when you start, again, using the wrong words, like I'm talking about this object spinning, well, the Earth spins in a particular direction, as seen from above the North Pole. It seems to be spinning in an anti-clockwise direction. Electrons can spin clockwise and anti-clockwise at the same time. Makes no sense whatsoever, but electrons don't care about us making sense of them. That's just what they do. So things are weird, not because things are weird, it's just because we find it difficult to understand them. Common sense is the collection of prejudices acquired by age 18. Common sense is simply the way we make sense of the world by trying to understand the world, and we've done that as children. We grow up with experience and we try and make sense of the world around us. Our brains are not wired to understand quantum mechanics. Our brains are wired after a few million years of evolution to try and work out where the next meal is coming from, or to work out whether that lion is going to eat us or not. Only in the last 100 years have we come up with the idea of this is the way the world is on the small scales, or we live in an expanding universe, so this is the way the world is, the universe is on the biggest of scales. Only in the last 100 years have we got to deal with that. That's why it seems weird, is just because we haven't got used to it yet. We've only been thinking about this for a century or so. When it comes to the idea of probability, some people said that's the way it is, and some people said no. If it looks like it's only a probability of something happening, then we're missing something. Einstein said God does not play dice. God is subtle, but he is not malicious. Other people said, well, maybe that's true, that we think we can work out the probability of something happening only because we don't know the underlying mechanism. But other people said, no, that's not the way it is. We can do a test and we are absolutely sure that the universe works on a probability basis. There is no absolute determination behind it all. So Einstein said, God does not play dice. But others, like Bohr, came along and argued with Einstein and basically said, stop telling God what to do. This is the way the universe is. It's built on probability. You, Einstein, don't like that and you think there's something else going on. But no, the universe is built on the idea of probability. That's the way it is. Deal with it. So Einstein never liked that idea, and others never liked that idea as well, and this was part of the argument in the early part of the 1900s. So let's deal with three aspects of quantum mechanics that hopefully bring home just how weird it can be. First, order matters. Not order versus chaos, the order in which you do things matters. And then we'll look at Schrödinger's cat, and then we'll have a look at a few images of atoms. So order matters. For those of you who remember your algebra, 2 times 3 is the same as 3 times 2. Algebra doesn't care about order. But in quantum mechanics, the order in which you do things does matter. So what, you might say? Well, let me give you an example of so what, based on the idea of what if the rules that we think apply in quantum mechanics at the smallest of levels, what if they applied at the macroscopic level? Let's imagine that we have a grassland on which 4 animals are roaming. The top pair, lion and vulture, are carnivores. The bottom pair, a waterbuck and an ostrich, are vegetarian. We can also divide them a slightly different way. There's the carnivores, there's the vegetarians. But alternatively, I could divide them up separately and say the ones on the left have got 4 legs, and the ones on the right have only got, have got wings. 2 legs, 2 wings. Okay, I know ostriches can't fly, but they've still got wings. Okay, so it still applies. So we've got carnivores and veggies, or we can separate them as 4 legs or they've got wings. Now, if quantum mechanics applies, we can say, let's go out into the savannah where there are only 4 sets of animals, 4 species of animal. Let's take those animals and let's pick 2 out of the 4. Let's, for instance, as an example, pick the vegetarians. We're going to take the vegetarians and we're going to put them in a separate corral. So let's take the vegetarians. We're going to take the waterbuck and the ostrich and we're going to put them in a separate corral. And then we're going to pick again. We're going to say, of those animals that we've now corralled, the vegetarians, let's pick those animals that have got 4 legs. So we would expect to get the waterbuck. What we actually find in the corral is waterbucks and lions. Even though we only put vegetarians in the corral, when we actually measure what's actually going on, let's pick out the 4-legged animals, as if by magic, the lions are back. Makes no sense whatsoever, but that is what happens in the quantum world. And not only is it weird, it's weird because if you choose the order differently, you get a different result. Let's do exactly the same again, but make a different choice. If we pick in a different order, let's pick the 4-legged animals. We see the species, we take the 4-legged animals, we take those away, and we put them in a corral, separate from the others. We then choose out of those 4-legged animals, the lion and the waterbuck, we now pick out the vegetarians. Now we would expect to only get the waterbuck. But what we actually find is the waterbuck and the ostrich. How did the ostrich get in there? It can't fly, so it can't have got over the corral wall. It's the same. Quantum mechanics says that's what happens. And yet, in common sense terms, we know that doesn't happen in the macroscopic world, and so we think it makes no sense in the quantum world. But in fact, that is how things actually behave. The mathematics of that is relatively straightforward to lay out, and arguably it makes it easier to explain in maths than it does in words, and that is part of the problem. Unless you've done the maths, you can't see how the maths is telling you that's the answer. What about a second aspect of weirdness, Schrödinger's cat? So here we're going to kill a cat. Let's not worry about it. It's not a real cat we're going to kill here. In Schrödinger's cat, it's a thought experiment, and it's an idea of you put a cat in a box, and then you put it in a box with a poison vial, which gets smashed by a robot with a hammer if it picks up that a radioactive atom has decayed. You set up the experiment so there's a 50-50 chance of an event which you can't predict actually happening, which will then result in the poison being released and the cat dying. I'm not sure if cats actually sweat, but okay, in this case. The point is, you close the box and then you wait till the length of time has expired until there's a 50-50 chance that the radioactive atom has decayed. And the question is, what state is the cat in? The radioactive atom, according to quantum mechanics, just like an electron can spin clockwise and anti-clockwise at the same time, the atom can be in two states at the same time. It can be in its original state, or it can be decayed because it spat out a radioactive element. Which means there's a 50-50 chance that the cat is alive and the cat is dead. But it doesn't simply mean we don't know which it is, because if the atom can exist in two states at the same time, that means the cat has to be dead and alive at the same time. If you accept the quantum principle of that's how atoms behave, then according to this thought experiment, what if that then resulted in the death of the cat? The answer is not simply that the cat is one or the other and we don't know until we open the box. That's not what it's saying. It's saying if we don't open the box, the atom is in two states at the same time, therefore the cat must be in two states at the same time. It must be in limbo. We can accept that for atoms. We find it very difficult to accept that for cats, because you never see a cat walking around that is dead and alive at the same time. And yet that is what quantum theory is telling us. This is part of the weirdness. We have to accept that we don't understand the full consequences of what this is actually telling us. Quantum theory appears to be correct, but it gives results that we struggle with from time to time. So why do we bother with quantum mechanics? Well, how do we know it's right? Well, we don't know it's right, but it's been with us for 100 years now, since 1930. So far, every test of quantum mechanics that's been applied in the last 100 years has shown that quantum mechanics is right. If there's ever a difference between what quantum mechanics says and what common sense says, common sense is always wrong. That doesn't prove that quantum mechanics is right. It simply means that after 100 years of trying, we have not found anything that shows a chink in the armor of quantum mechanics. So maybe something better is going to come along one day, but for the last 100 years, it's proved extremely valuable for us to understand how things work. And indeed, there are plenty of examples where not only does it disagree with common sense, it also disagrees with what Isaac Newton would have said. If we ask what's going to happen if we send this particle into that particle, Newtonian mechanics would say this is going to be the result. Quantum mechanics says something different. When we do the experiment, we get the answer that quantum mechanics says, not the answer that Isaac Newton says. So it's the same argument. At the moment, everything points towards quantum mechanics being right, or at least right until something else comes along, and therefore that's why we believe it's correct, and that's why we are happy to keep on using it for perhaps another 100 years or so. And rather surprisingly, perhaps, we can actually use quantum theory to actually build a microscope that works on quantum principles. It's called a scanning tunneling microscope. I'm not going to go through all the details, but if you take a sharp needle, and this is the bottom of the needle, so you have to imagine there's a few zillion atoms above this very sharp tip, and it's coming down close to a particular slab of material, of which some of the atoms are shown in light blue here. It doesn't matter whether the material is a metal or a semiconductor, it really doesn't matter. What matters is if you apply a voltage between the two and measure how much current flows, according to Newtonian mechanics, according to simple circuit theory, no current will flow until these two touch. In other words, until D equals 0, and then current can flow around that loop. But quantum mechanics says, even though there's a gap, current will flow, and the current that flows will be very sensitive to just how big that D, how big the distance is between this tip and the sample that you're coming close to contact with. And using that, we can build a microscope, because if we make a nice sharp tip, if we move it horizontally, the distance to the surface, if the surface is not atomically flat, and even if it's atomically flat, it's still effectively bumpy because it's made of individual atoms, then D effectively changes, and so the current changes. The microscope is actually more likely to be used in this mode, in which the tip moves across the sample and we move it in such a way to keep D constant. In other words, we measure the current and have a feedback loop that keeps D the same. So moving the tip across the sample effectively allows us to map out the sample, and if we have the sensitivity, we can literally see the individual bumps of individual atoms on the surface if we have the right amount of sensitivity. So there's a handsome physicist in front of one of these scanning tunneling microscopes, which is in this vacuum chamber in the background there. It's in a vacuum chamber to keep everything nice and clean. We don't want any oxygen or nitrogen or carbon dioxide getting in the way of our experiment. So we put it into a vacuum vessel at about 10 to the minus 13 atmospheres of pressure. And then we can obtain images. This is an image from a colleague of mine in the University of Manchester. It's the surface of rust. And notice the scale bar at the bottom, 2 nanometers on the scale bar there. And here, the vertical scale of this particular image has been exaggerated to make the atoms a little bit more clear. So each bump, each little mountain peak is an individual atom on the surface, probably oxygen. This is rust, and it's actually a combination of 2 iron oxides. It's Fe2O3 and Fe3O4. And I can't remember now which way round it is, but notice there's a whole island of atoms here arranged in a particular pattern, and another island and another island. And if you look at where those islands are, they are arranged in a pattern as well. And in between those islands in which the atoms are very prominent, there seem to be rather flat regions. And it's thought that what we're looking at is iron oxide of one type, Fe3O4, where the oxygens show up rather dramatically, and Fe2O3, where the oxygen atoms don't show up quite so dramatically. That depends on the technicalities of how we do the scanning. But the point is that we can see individual atoms, and we get resolution that's way better than 1 nanometer. So we definitely have the resolution to be able to resolve, given that atoms are typically about roughly a tenth of a nanometer or so. We can image the positions of atoms. What we're actually doing is imaging the average position of the atoms, because the atoms will be moving all over the place. So we're effectively averaging the positions in these sorts of images. And we see patterns whenever we use scanning tunneling microscope. The previous image was rust. This is a particular alloy of different metals. And one thing you notice is that there's no obvious rectangular structure to the positions of the atoms here. There's no hexagonal structure, but perhaps you notice that there are pentagonal structures. Occasionally we see daisy flowers of a group of 10 dots. Occasionally we see groups of 5 dots. The atoms are arranged in this structure, which explains why, when this structure decides to crystallize, it ends up as a dodecahedron, because the atoms want to arrange themselves in pentagons. And if the atoms want to arrange themselves in pentagons, when it crystallizes, if you do it properly, you can end up with a crystal which has pentagonal faces and ends up as a dodecahedron. If we look at the distances between atoms, which we can do with these microscopes, we actually find that there are lots of different distances, and a particular ratio, a ratio of this distance to that distance, keeps cropping up a particular number, the golden ratio of 1.6 and a bit. And that's the same number that crops up in pineapples, for instance. If you were to count how many scales there are in a pineapple going spirally in one direction or spirally in the other direction, the number, when you divide one by the other, gives you a number like 1.62 or thereabouts. It's also the same for sunflower seed heads. If you count the number of seed heads by following a spiral in one direction and then following a spiral in the other direction of these two counter-rotating spirals, if you work out how many seeds are in the seed head, you find the ratio of the two comes out to be about 1.62. So some reason or another, the arrangement of atoms at the very smallest scales is sometimes reflected by what's happening in nature at much larger scales. And understanding why that should be is what some people are doing, either in material science or looking at the properties of materials, trying to understand why atoms want to arrange themselves in particular ways that sometimes is mirrored by how small objects in nature want to arrange themselves. And this gives you an idea of, again, this confusion. Are we talking about particles or are we talking about wavy things? Here, a scanning tunneling microscope image, which has been color-coded to give us a little more information. What we've actually done here, again, not me personally, what these people have done in Zurich is take a whole load of atoms, arrange them in a circle. I'm not going into the details of how, but if you basically make a corral by putting a lot of atoms in a circle, we can see those atoms appearing as these sort of orange mountains. So it appears that these atoms are behaving like particles because we've effectively moved them into position and we've made a big ring of them. But what's going on inside the corral? Inside the corral, whatever's going on, it seems to be behaving like a wave. If you imagine that as a pond of liquid, what would happen if you threw a stone into the middle? It would produce waves, and it would produce a circular pattern of waves, much like this pattern that we've got here. So this one image appears to be showing us things at the quantum level, some of which are behaving like particles and some of which are behaving like waves, even though essentially everything we're imaging here are the electrons in atoms. But sometimes they behave one way, sometimes they behave another way. Despite the fact this may have been taken on a Monday or a Tuesday or a Wednesday, still we get both of these things appearing. And that so-called wave-particle duality is part of the weirdness of quantum mechanics. If quantum mechanics hasn't shocked you, then you really haven't understood it. The other famous quote is, if you think you've understood it, then you haven't understood it. The other quote I give to students is, nobody understands quantum mechanics. But that isn't an excuse for not passing the exam, of course. So, it was confusing 100 years ago. It's still confusing now. Some people say the mathematics works. Trying to figure out what it all means gives you a headache. But the mathematics always works. So one attitude is shut up and calculate. Basically, trust the maths. The maths gives you the right answer. If you can't visualize what the maths is telling you, doesn't matter. The maths is right anyway. And part of the problem is just us getting our heads around what it all means. So quantum mechanics has been exceptionally useful for the last 100 years because it has allowed us to calculate and do all sorts of things, like manufacture electronics with transistors that are barely a few nanometers in size. We wouldn't have an iPhone if it wasn't for quantum mechanics because we wouldn't be able to do that. That's just one tiny example of what it can do for us. But one of my favorite quotes is actually from Einstein. The most incomprehensible thing about the world is the fact that it's comprehensible. The universe doesn't owe us anything. There's no reason why a monkey that was swinging around in trees 1 million years ago should be able to understand quantum mechanics or an expanding universe. And it is quite possible that in other situations where life evolves, you don't find primates that end up understanding how quantum mechanics works. So it is absolutely incomprehensible that we have even the slightest chance of understanding quantum mechanics, or at least being able to set up a structure that allows us to calculate how things are supposed to work, what would happen if I do this experiment, what would be the wavelength of light I see if this molecule behaves this particular way. So the fact that it is comprehensible, that still takes a little bit of work to deal with the maths, to think about what's going on, to try and work out whether the cat is dead or alive. It still takes a little bit of thinking about, but it is not totally incomprehensible. Yeah. So we have a little bit of thinking to do. We've only been thinking about this for 100 years, remember, and it might take a few thousand years before evolution rewires our heads in such a way that we can get a better handle on what this is all telling us. So let me just finish with this image. Notice the scale. The scale here is the total image is less than 1 nanometer. This image is 850 picometers on a side. A picometer is 1,000 times smaller than a nanometer, which is 1,000 times smaller than a micron, which is 1,000 times smaller than a millimeter, 1,000 times smaller than a meter. And we can see blobs, and we interpret those blobs as, well, they're probably atoms. The atoms of carbon, if we think about how many carbon atoms there should be in a gram of material, these seem to be the right distance apart to be individual atoms of carbon. And so with scanning tunneling microscopy, we can indeed see individual atoms. And to bear in mind the magnification we're looking at here, on this scale, a grain of sand would be about the size of the moon. That gives you an idea of how much we've zoomed in to see individual atoms. And whenever I see a scanning tunneling microscope image which shows individual atoms, I remind myself just how big a grain of sand would be, and I remind myself about the William Blake poem. See a world in a grain of sand and heaven in a wild flower. Hold infinity in the palm of your hand and eternity in an hour. Thank you all very much.